Here we have one of my favorite problems. I call it the Rotor of Doom. So this is a machine you might have ridden on in an amusement park. I did when I was a kid. I cannot any longer. Where you sit in a big cylinder that then starts spinning, kind of like a washing machine. And as it goes faster and faster, you kind of feel yourself push to the wall. You're really feeling the member of the wall pushing on you, keeping you going in a circle. And when it gets up to a certain speed, they drop the floor and you actually stick to the wall. You don't fall with the floor. So we want to figure out in this case, how fast does one of these things have to spin for you not to slide down the wall? In this case, I'm going to first start off by making just a few, labeling a few variables. Let's say your mass, you have a mass of m. There's a coefficient of friction of mu between you and the wall. This thing has a radius r. We're going to solve for an omega. And I think that's all that we need. If we need something, we'll assume we're on Earth. So if we need g, g is g. So again, we'll first start by drawing a free body diagram. So here you are. Now let's think, this is a little bit weird situation because you're not standing on a floor this time. The floor is gone. So if we think about the forces acting on you, the surface pushing on you is not the floor, it's the wall. So we have a force, a normal force pushing out of the wall on you. We have the earth is still pulling on you, so we have a gravity force going down. But this time, the thing that's holding you up, keeping you from falling, is actually friction. You're interacting with the wall through a friction force, then that's keeping you sliding due to gravity. So we have an upward acting frictional force here. And that's pretty much it. So if we do a sum of the forces equation, in the center seeking direction this time, so we're going to call towards the center positive, we're going to get the just the normal force equals ma, and this is our centripetal acceleration, so MAC. And if we do a sum of the forces in the y direction, we have our friction force minus our normal force, and we don't want you moving in the y direction, so that equals m times a in the y, but we want that to go to 0. No acceleration in the y this time. And now we just have to solve these two equations simultaneously, and we should be able to figure out how fast we need to rotate this thing. So first, let's start off by just substituting some of our smaller equations. So we can turn our y equation, we can say this is really the coefficient of friction times the normal force. Oops, I just realized I made a little mistake. That's not the normal force, that is g up there. Coefficient of friction times normal force minus mg equals 0. And in our centripetal equation, we can have the normal force equals, and this time I'm going to use the omega version because we're asking how fast does it have to spin, not how fast is it going on the outside. So I'm going to use m omega squared times r for my centripetal acceleration this time. And as you can see, it's almost already set up. Our centripetal equation is already solved for the normal force, so we can just sub this in to our y equation, which turns into the coefficient of friction times m omega squared times r minus mg has got to equal 0. And now we can just solve this for, we're looking for omega, so we know the masses drop out this time. So we bring g to the other side, do a little division, we get omega squared equals g over mu r, and we get omega equals the square root of g over u times r. And if we do a quick check of our units just to make sure we did this correctly, it's always a nice way to make sure when you're doing algebra, or getting answers algebraically, that at least this is one check you didn't make a mistake. So let's see, we got units of meters per second squared on top, divided by, let's see, mu has no units, divided by meters, meters drop out. So we have the square root of second squared, which gives us per seconds, and that's what omega is in. So it looks like we probably did our answer right. So we get that the speed you have to spin at so that you do not fall down is equal to the gravitational constant on your planet divided by the coefficient of friction times the radius of your tub that you're spinning in and the square root of that. So as we can see, again, the bigger the gravitational constant, the faster you have to spin. There's more force that's actually pulling you down. The rougher your surface, the bigger the mu, or the more frictionful your surface. Doesn't have to technically be rougher. The less omega you need, you don't have to spin as fast because your friction is kind of more efficient, I guess you could say. And the bigger the radius you spin in, you actually need less omega too.